All right, so we just finished up talking about acid and base chemistry that involves movement of protons, right? So Bronsted and Lowry described acids as molecules that donate protons. Bases are molecules that accept protons. Oxidation and reduction's the other side of a similar story. However, historically, it wasn't defined well. So let's start out with the historical definition. So historically, oxidation meant simply something gains oxygen, right? So it reacts with or gains oxygen. We know today that it's a lot more complicated than that, but that's where the term oxidation comes from. It has that prefix ox in there to account for oxygen. Reduction means, or historically meant that you were removing oxygen. Oh my goodness. From a metal or non-metal oxide. So if you're gaining an oxygen in a chemical reaction, typically that's thought of to be an oxidation. If you're removing oxygen, it's a reduction. Yep?
Is this because oxygen has some particular special property, or because it was particularly common, or because everybody working on this was an organic chemist?
No, this is a great question. So if we think about our atmosphere, right? Our atmosphere on planet Earth has a fair amount of oxygen in it. Do you remember what percent based on the oxygen lab? It's about 15 to 20% depending on the elevation that you're at. So if we're in an atmosphere full of oxygen, we do a lot of chemistry with oxygen. That's why it was really well studied. And it's not just organic chemistry, right? So if you think about iron, iron is a metal. If you leave iron out in a high oxygen environment, what happens to it? It can rust, right? Which means it's oxidizing, right? You're forming iron oxide, so that would be an oxidation of iron. So we're going to talk more and more about that, but historically they were really looking at the addition or removal of oxygen. This works for a lot of situations, but not all situations. So we're going to do a modern definition. All right, the modern definition is much more generic. It says that oxidation is loss of electrons from a molecule, where reduction is gain of electrons. So if you're pulling out electrons from a given molecule, you'd be oxidizing it. Same is true for an atom. If you pull out electrons from an atom, you'd be oxidizing it, whereas if you put electrons in, it'd be reduction. So this does confuse people, but I've got a mnemonic that tends to help, and that is oil rig. It's pretty simple. Oxidation is loss. Reduction is gain. So this is what got me through general chemistry, is remembering oil rig. If you remember that mnemonic, you can remember oxidation is always a loss of electrons. Reduction is always a gain of electrons. So it's a pretty simple tool. All right, so let's kind of summarize what's going on here using both definitions. All right, so first thing first, we know oxidation, like we just said, is loss of electrons. That's true for all oxidation reactions. Reduction, on the other hand, is gain of electrons. And oxidation, we said often, but not always, has a gain of oxygen. Where conversely reduction, we said often, but not always, has a loss. It's pretty simple. There's also something else you can look at too. Yep.
Is the reason that these terms are interchangeable, oxidation with the gain of oxygen and the loss of electrons, is that because oxygen is so electronegative, or?
Yeah, it has a lot to do with the reactivity of oxygen, its electronegativity. There's a lot going on that's, to be perfectly honest, kind of beyond the scope of this course. So I'm not going to jump down that rabbit hole right away. But if you go on and take general chemistry, you'll talk about it in more detail. Yeah, that's a good question though. All right, so like I said, the true definition has to do with movement of electrons rather than movement of protons, right? Acids and bases, we look at movement of protons, but in this case, we're looking at movement of electrons. All right, so I'll show you how to do some of this, and it does get a little bit tricky, so you'll have to bear with me. But we essentially have to count electrons in our system to determine whether or not we're gaining or losing them. So I'll give you some hints first. Hint number 1. Elements by themselves are considered neutral. Count as 0. And I'll show you what I mean by that with some example problems. Okay? Hint number 2 is that treat all other elements as ionic. So what I mean by elements by themselves, that could be something like a sodium atom by itself, or it could be something like H2. H2, hydrogen gas, is elemental hydrogen, meaning it's only made up of one type of element. However, if you've got a combo of more than one type of element, that's when you follow rule 2. Does that make sense? We'll treat those as ionic. And then 3, I'll show you the trends. Let's do this. We've got oxidation going up. We've got reduction going down. So we've got 2 competing trends. When we're oxidizing something, meaning going up, are we gaining or losing electrons again? So oxidation is loss or gain? It's loss. So oil rig, the oil means oxidation is loss. So as we're going up, we should be losing electrons. And then down here, we said that this is going to be gain of electrons. All right, so just really generically, what happens to an ion if you lose electrons? Do you get more positive or more negative? More positive, exactly. Conversely, if you gain electrons, you're going to get more negative. And somewhere in between positive and negative, you're going to have neutral, right? So if you're going from a neutral atom to a positive atom, meaning a cation, that means you're probably going in that upward oxidation direction. Versus going from neutral to more negative, you must be gaining electrons, which means it's a reduction reaction. So sometimes I like kind of showing these simple diagrams to help understand what's going on here. All right, but let's try to apply these using some examples. And in fact, let's do the rusting example of what happens to a steel tool if you leave it out in your yard for maybe a week or so. Actually, I'm going to stop and do it this way. So we've got iron and steel. We've got oxygen in our atmosphere. This is O2. And then over here, we're going to make Fe2O3. So first of all, I want to do a little bit of review. First thing I want you to do is to bounce this equation. So right now, it doesn't look like we've got the same number of atoms on the left-hand side versus the right-hand side. So let's bounce it first. So what do you think I should do to the iron? Put a 2 in front of it, right? All right, now I've got 2 irons on each side. I've got 2 oxygens on the left. I've got 3 on the right. That's not going to work. So what might I do to fix that? Double the most complicated molecule. Okay, so I'll double this, which means I should probably also double my iron, right? So now I've got 4 irons on the left, 4 on the right. Now I go back to the oxygens. I've got 6 oxygens on the right, but only 2 on the left, which means I can fix that by adding a 3 in. So oftentimes when we're doing redox reactions, we do need to be careful that we're using balanced reactions, just like with any other sort of chemistry. All right, second question before we do the redox. Let's name this compound. So let's break this apart. And we know it's ionic because it's a metal and a non-metal. So I've got Fe, 2 iron atoms. We've got 3 oxygen atoms. What charge does oxygen always have when it's ionic? It's in group 6A. So it's 2 away from a noble gas, so it must be 2 negative. Which means our irons must be what? 3 positive, right? That way our positive charges cancel out our negative charges. And let's go ahead and name this. Would it just be iron oxide, or would I call it di-iron trioxide? What would be the appropriate name for this? Yeah, so in this case, we've got a transition metal. So we would name this iron. To indicate that the charge is 3 for that iron, we'd put Roman numeral 3, and then we'd say oxide. So if you leave iron out in your yard, typically becomes mostly iron 3 oxide, not another oxidation state of iron. All right, so now let's do kind of another breakdown. So in the first hint, I said treat individual elements as neutral, right? So over here, I'm going to go down and I'm going to say, all right, this iron essentially is neutral, so I'm going to put a little 0 up there to indicate that it's not positive, it's not negative, it's just a happy neutral iron atom, right? So not positive, not negative, therefore not a cation or anion. All right, so now if we look at this, we can say, all right, iron in this reaction went from neutral iron to iron 3+, which means what happened? Did it gain or lose electrons? Lost. So each iron atom lost 3 electrons, right? All right, so if we think about iron in this reaction, was it oxidized or reduced? Oxidized. All right, so that makes sense. And then over here, let's go back up and focus on our oxygen. Oxygen is by itself, meaning it's only bound to other oxygen atoms. It's not a true compound, it's elemental. All right, so that means oxygen in this case is going to be treated as being neutral as well. And then over here, we said that the oxygen was going from neutral, meaning no charge, to oxygen that's ionic with the 2 negative charge, so it must be gaining electrons, right? So each oxygen gained 2 electrons, which means oxygen was reduced. All right, going back to that historical definition, this works out pretty well, right? So if we think about iron, iron in this case picked up an oxygen atom, which means it was oxidized according to the historical definition, where oxygen, on the other hand, was O2. That means it got ripped apart, it lost some of its oxygen atoms, which means it must have been reduced in this situation. But typically the best way to go about it is to basically keep track of your charges from the beginning to the end and then determine whether or not you gained or lost electrons in that reaction. Does that make more sense? Why do you think these sorts of reactions are incredibly important? Think about your lab yesterday. What can we do when we move around electrons? We can create energy, we can transport energy, we can utilize batteries. In fact, this is actually an important biological process in your cells as well. This is how your cells produce energy, is by moving electrons and protons around. So it's important in biology, it's important in batteries. Without the movement of electrons, life would not exist. So it's pretty important and interesting, but kind of tedious tracking all these electrons. All right, so let's do another one. So in this one, I'm going to start out with CuO plus zinc. And we're going to make, ZnO plus Cu. All right, just to review, what would we call CuO?
Copper 2 oxide.
Yeah, it'd be copper 2 oxide. If we were to break this down, we know that oxygen as an ion is always going to be O2 negative, right? Because it's 2 away from being a noble gas. Where for copper, in order to balance out that 2 negative for the oxygen, copper must be 2 plus. So I'm going to put that on the bottom just to keep them separate from one another. All right, now let's go over and look at the zinc. And I'm going to include a different color for zinc. What charge would we put for zinc in this situation? First of all, should we treat it as ionic? Or should we treat it as neutral? Neutral, it's by itself. So in this case, I would say this is zinc 0. Okay? So we've counted the charges for our copper, our oxygen, and our zinc, and gave those charges in the top right-hand corner. Now let's go over to the other side. Over here, let's start with the oxygen. What charge will the oxygen have in zinc oxide? -2. All right. So if we look at this oxygen, going from there to there, did it gain or lose electrons, or did it not transfer electrons at all? Yeah, so I would say no loss or gain. Oxygen is just kind of hanging out in this reaction. So it's neither an oxidation nor a reduction reaction. All right, let's do the same thing with zinc. What charge will zinc have? Must be 2 plus to cancel out the 2 negative in oxygen. All right. So let's go ahead and track the movement of electrons for the zinc. We know something changed, right? It went from being 0 to 2 positive. So did it gain or lose electrons? Must have lost electrons, right? Because electrons have that negative charge. So zinc lost electrons. Specifically, it lost 2 electrons. So was it oxidized or reduced? Oxidized. And in fact, I'm going to highlight that because that's one of the main things I want us to keep track of, is which elements were oxidized or reduced in this reaction. All right, we're not quite done though. We got to consider the copper as well. What will the charge be for this copper? 0, it's by itself. All right, so copper started out as 2 positive. It ended up being neutral. Let me fix this arrow. Did it gain or lose electrons? It must have gained electrons to eliminate the positive charge, right? So copper gained electrons. That means that copper was reduced. So we can highlight this as well. The other kind of interesting thing too, like I said, we can't create or destroy things in chemistry. If we think about the zinc, we had one zinc atom, and how many electrons did it lose? It lost 2 electrons, all right? And if we think about the copper, how many electrons did the copper gain? 2. So we have to balance out those electrons just like we balance out any normal atom when we balance reactions. So it can get kind of complicated, but like I said, the main thing I want you to know is which atoms were oxidized or reduced. And then tomorrow I'm going to have a nice long worksheet for you to work on as well. All right, let's do a few more though, because this does trick people. All right, this next one is magnesium reacting with chlorine gas to produce magnesium chloride. You notice in this one, unlike the other ones, there's no oxygen anymore. So using the historical redox definition of gaining or losing oxygen, we couldn't solve this, but we can solve this by tracking electrons. So let's start with magnesium. What charge will magnesium have on the left? Neutral, it's by itself. So I'll just write Mg0. And then let's go to the chlorine. What charge will that chlorine have? 0, it's by itself too. So I'll plug that in. Then we'll go over to the second magnesium over here. What charge will magnesium have if it's ionic? 2+, it's in column 2A. And then let's just finish up with the chloride. If chlorine is ionic, meaning not by itself, what will that be? It'd be 1 negative, right? It's 1 away from being a noble gas, so it'd be 1 negative. Okay, so now we can track electrons pretty easily. Yeah?
So you put 1 negative and the 2, like the subscript 2 doesn't matter when you're doing this?
Yeah, that was a good question. So you're asking about the subscript 2. What that essentially means is that we just have 2 chloride atoms floating around, each with a 1 negative charge. So it just indicates each of those chlorines must be 1 negative. Oops, shoot, I didn't mean to erase that one. All right, so now let's track the movement of electrons. In the top one, did the magnesium gain or lose electrons? It lost, right? Electrons are negative, so if you lose them, you become more positive, right? So the magnesium lost 2 electrons, therefore it became magnesium 2+, which means that magnesium was oxidized or reduced? Oxidized, according to oil rig. So we can highlight that and keep track of things. Knowing that, what do you think's happening to the chlorine without even checking? It's got to do the reduction half, right? So oxidation is paired with reduction in these systems. All right, so if we look at chlorine, it went from being 0 to -1, which means each chlorine atom must have gained 1 electron, right? So we could say each Cl gained 1 electron, which means that chlorine was reduced. So we can highlight that as well. And just like I said before, we can't create or destroy electrons in the system. So the magnesium, that one individual magnesium atom, lost 2 electrons. And then we had 2 chlorine atoms, each of which gained 1 electron. So it was a net movement of 2 electrons kind of in each direction, crisscrossing. Does that make sense? All right, we'll do one more. And then I might actually let you out early. Assuming we get done early. All right, so let's start with magnesium and nitrogen. And when you react this, you get magnesium the subscript 3, and then nitrogen with a 2. What would we call that final product? It's ionic, so we don't need mono, di, tri, and so on. It'd be magnesium nitride. So if you react magnesium metal with nitrogen gas, you can create magnesium nitride. If I look at this, though, it doesn't look balanced at all. So we got to fix that. So it's a pretty simple fix. We have 1 magnesium on the left, 3 on the right, so we'll plug a 3 in here. We have 2 nitrogens on the left, 2 on the right, so it looks balanced to me. Okay, so now we can go ahead and we can say magnesium is by itself. Anytime you have an element by itself, not bonded to other elements, it's going to be 0. If we think about nitrogen, it's also by itself, so we'll treat this as nitrogen 0. Then if we go over here, now magnesium is bonded to a different type of element, so what would the charge be for magnesium? 2 plus, right? It's in column 2A. So as an ion, it would prefer to lose 2 electrons to have an octet. Versus nitrogen, if you look at nitrogen, it's in group 5A, 3 away from a noble gas. It would prefer to be -3 or steal 3 electrons. Okay, so now we can track our movement of electrons. All right, so magnesium, did it gain or lose electrons? It must have lost electrons. So each magnesium lost 2 electrons, right? We had 3 magnesiums, each of which lost 2, so it looks like a total transfer of 6 electrons. That means that magnesium was oxidized or reduced? It was oxidized. All right, so we can go ahead and highlight that just to keep things organized. And then nitrogen down on the bottom went from being neutral or 0 to 3 negative, so it must have gained 3 electrons. And we've got 2 nitrogens. Each nitrogen gained 3 electrons for a net total of 6 electrons, which is good. We want those to cancel, which means that nitrogen was reduced. All right, so that's where I think we're going to hold up today. But the textbook does have a lot of good practice problems in there, so if you are having trouble with this, either meet with me, go to the Writing and Tutoring Center, or try to read through your textbook and do practice problems. Yep?
I'm noticing all of these reactions are formed compounds. Do all reactions?
Yeah, that's a good question. Not all redox reactions produce ionic compounds, but when we're counting electrons for redox chemistry, we treat them as ionic even if they're not.
Okay.
Yeah, great question.
And all formations of ionic compounds are redox reactions. Like if you go from 2 atoms to
Yeah, if you go from 2 elemental atoms and make an ion, it's got to be a redox reaction. Yep.